Hello, welcome to a coding challenge. And I can summarize this coding challenge very quickly in one sentence. This is a spinning cube. It is a three-dimensional cube that you are seeing on your two-dimensional screen. I am able to create this three-dimensional cube because I am using the P3D renderer. Processing, Java-based creative coding development platform thing. I can make 3D stuff using the P3D rendering engine and then functions like box and rotate X and rotate Y and rotate Z. And that is how I get this. But how does this really work? How does the processing even make this happen? I am going to do the most basic simple thing. I said one sentence and I'm like 12 sentences. I'm like 200 sentences in if I'm being perfectly honest. I am going to change this from P3D to P2D. I'm going to eliminate all of the 3D rendering capabilities. I'm not going to allow myself to use any of them, and yet I'm going to recreate exactly this same visualization. I'm going to do matrix rotations, projections, those types of things. So this is not going to be comprehensive, like how to build a 3D engine with ray casting or ray tracing and lighting and shadow and all sorts of like complicated stuff. I'm going to just do the basics just to create this 3D illusion in 2D, really because if I can use the P3D, if I can create the 3D illusion and render it into 2D space, what if I create a 4D shape and then render it into P3D space, right? If I can project a 3D object into 2D space, there's no reason why I couldn't project a 4D object into 3D space. And then I don't know, my computer's gonna melt and I'm never gonna make any videos again. But I'll just stick with this. Okay, so let's begin coding. So I am going to I'm gonna hit save, and I'm gonna take out all of this 3D stuff. I'm gonna leave translate, stroke weight, no fill. I'm not gonna be able to use these anymore. I'm not gonna be able to use these anymore. I'm gonna leave all this. I'm in P2D. I'm going to take out P2D. It's nice to sort of say that. The default renderer is also a 2D engine, so I don't need to actually say P2D. Now, I should also mention that in this particular video, I'm making use of a few functions I've previously written. I actually might have a video. I definitely did it on a live stream. So either way, in the video's description, I'm going to link to where you can watch me code all these functions. But what these functions are for certain matrix operations that I'm going to do. Don't worry. I will talk about what they are when I use them. So the first thing that I want to do is let me just get some points on the screen. How am I going to do this? Let me make so I'm going to make pretty heavy use of the p vector object, and I'm going to say I'm going to make a array of p vectors that just has 4 points in it, and I'm going to say points index 0 is a p vector at, and I'm just going to build a little square. So I'm going to say the first one is at like -50, -50, and then the second, third, fourth is at 50, -50, then 50, 50, then -50, 50. These should be the 4 points of a square. So what I want to do here now is just say for every vector in points, just draw a point at v.x, v.y. So now, but these are, the whole point of what I'm doing is I can't do this, right? So these are actually going to be 3D. The point of this is they're going to be in 3D. Bear with me for a second. Well, all will come to pass. Those are going to be 3D points, but right now I haven't done anything 3D yet. Let's make the stroke weight quite a bit bigger so I can see them. There we go. So those are my 4 points. So first, what I will need to do, and actually, I'm not going to worry about this part right now. Okay, so what do I need to do to make a 3D engine? Okay, here's the thing. I'm going to search for some props. Okay, I found some props. I'm actually going to turn this light off too. And I'm going to try to do a demonstration in the dark. This is a 3D object. It is the book a million random digits with 100,000 normal deviates. The way that a 3D object is rendered on a two-dimensional screen is through something called a projection. That projection you can think of as basically like a shadow. So if I have this book here and I shine this cell phone flashlight, you can see that there's a projection onto the wall. It looks like a square. If I rotate this, it rotates. If I rotate it around the y-axis, well actually I have to do this. If I rotate it around the y-axis, you can see it starts to become thinner. I can rotate it around the x-axis. It does this. So, so this is the idea. I need to create this same exact, I need to create that same exact idea, but in code. And the way that that's done is with something called a projection matrix. So the point, the 3D point, is actually something like this. It's a matrix that has x, y, and z in it. This is actually 3 rows by 1 column. This is something that I've gone over in other matrix math videos, and here's a kind of a summary of it. A projection matrix, if I'm projecting into 2D, right? If I'm projecting this 3D point into a new 2D point, what I need is a projection matrix. Now here's a really simple projection matrix. This projection matrix has a 1 in the x spot, a 1 in the y spot. X, y, z, and it has both zeros in this sort of z column here of this projection matrix. What this is actually always going to do is give a two-dimensional matrix, not two-dimensional, sorry, a 2-column matrix with just the x and y. This projection matrix just eliminates the z. And actually, this will get us pretty far. In fact, this exact matrix is what's known as, is what's used for like orthographic projection. There's all different stereographic and all different kinds of projection matrices. This one is going to work just fine for us. So let's put this in our code. Okay, so the first thing that I need to do is I need to create that projection matrix. And this is actually an easy thing. Now, of course, if I were doing this in a more sort of robust way, I'd probably have like a matrix math library. I just have a few matrix math functions that are in this tab that I wrote in a previous video. So I'm going to say, make a projection matrix, and I'm going to just make it as a two-dimensional array. So 1, 0, 0, comma, 0, 1, 0. So this is my representation of a 2-row by 3-column matrix. 2-row by 3-column matrix, that is this right here, represented as a two-dimensional array. Now, what I'm going to do here is I am going to say for every point, for every 3D point here, let me move this over a little bit. So what I want to do, okay, so what I want to do here for every single 3D point, right, is, and this was sort of pointless that I did before. What I want to do is I want to create a p vector. I'm going to call it the projected 2D vector. And what I'm going to do is I'm going to say matrix multiply the projection times v. So this is what I want to do. To project a 3D point into 2D, I need a projection matrix, which I just made, and then I need to matrix multiply the projection matrix and the vector. Now, how the math for that works involves this times this, plus this times this, plus this times this goes here, and this times this, plus this times this, plus this. I'll refer you to matrixmultiplication.xyz. That website has a nice visualization, and I've made other videos about how matrix multiplication works, which I'll also link to. But I'm just going to assume that matrix multiplication works. And you can see how this makes sense. This one leaves us only with the x. This one leaves us only with the y. So now I'm going to then say point projected 2D x, projected 2D y. I probably could come up with a better name than that. And now if I run this, same exact thing, right? Because in this case, it's as if the point light and the place that I'm projecting onto and the thing, they're all like kind of in exactly the same spot. So there's no skewing. There's no skewing of the sort of perspective. So if I were to move that light around and change the projection matrix, different things can happen. But I'm not going to worry about that right now. What I want to do now is see if I can apply some rotation. Okay, so how do I apply rotation? Well, I know that I could just say like rotate by angle. Right? If I say rotate by angle, processing is going to do that transformation for me. But what if I want to rotate x, rotate around the x-axis? I can't do that. I'm getting some sort of error somewhere or nothing. It should say not available with this renderer. Oh yeah, rotate x can only be used with a renderer that supports P3D. I need to write my own rotate x function. And guess what I need for that? Rotation matrix. I think the ding is better after. Guess what I need for that? Rotation matrix. Oh yeah, that was great. That was exactly what I meant to do. Okay, so now I am going to create a rotation matrix. Now how does that work? Luckily for me, I already have this Wikipedia page opened up. Look at this. A rotation matrix is a matrix that is used to perform a rotation in Euclidean space. And this kind of makes sense, right? Look at this rotation matrix. Have you ever done one of those things where you do polar to Cartesian coordinate transformation and you take the angle and you keep increasing the angle and then you convert that to x and y points and you have this like spiraling thing? I've made videos where I do that. Basically, to rotate in 2 dimensions, this is all I need. So just for fun, let's first just do this. I'm going to say float. I'm going to make another. I'm going to call this rotation, and I'm going to make another matrix. And I'm going to do exactly this. It's going to be 2 by 2, and it's going to be cosine theta and negative sine theta. And I'm calling it angle. Cosine angle, negative sine angle. And then it's going to be, what was it? Sine angle, sine angle, cosine angle. Is that right? So this is, I didn't get this right. There's this needs a bracket. I don't know what I'm doing here. And this needs a bracket, right? It's a 2-dimensional matrix. There we go. Nope, semicolon. There we go. So this is my rotation matrix. This is my rotation matrix. So what now? What if I were to say, okay, now I'm going to take out this rotate x. I'm not using the native rotate function. And I'm going to say p vector rotated equals mat mul rotation times projected 2D. And now I'm going to draw the point at rotated. So I am projecting, V is a 3D vector. I'm projecting it into 2D, and then I'm rotating it, just a 2D rotation. And if we run this, okay, what's wrong? Columns of A must match rows of B. Oh boy, I made a problem. Okay, something horrible happens. I got columns of A must match rows of B. I made a mistake in my matrix multiplication thing. Here's the thing, I'm trying to be all clever to show you it in 2D first. The truth of the matter is P vectors, they're 3D. Even if I'm drawing just the X and Y, there's always that Z component. So I actually need to include this extra column with zeros in it to do this demonstration. So now you can see that's me doing 2D rotation. And actually, I'm actually doing 3D rotation, right? Because really, what this should be is this. This is what I would call XY rotation. I am rotating around the Z axis by, using the X and Y axes, right? Look at this. Now I'm going to say, so this is what, and if I kept scrolling down this Wikipedia page, we would see this. We would find this right here. This is the one that I'm doing. Rotation Z, right? Oh, I need a 1 there, of course. Not a 0 there. Very important. I don't want to lose the Z point. I want to rotate the X and Y axes around the Z axis, but I don't want to lose the Z point, so I need a 1 there. In the 2D case, okay, so I need this here. So this I'm going to call rotation Z. And now I'm going to make some other ones. Let's call them rotation x. And the rotation x is y and z. So I need to have my rotation values in the y and z spots. So hard to do this. I should just copy it from somewhere, but this will work. And I think this is right. So this should be, right? You can see this is, my spacing is off, help me. This was rotation z, this is rotation x. And let's do one more. Let's do rotation y. So I need to have 0, 1, 0 in the middle. The last one will be sine of angle, 0 cosine of angle. And the first one will be cosine of angle, negative sine of angle with a 0 in the middle. Okay, so this should all line up nicely. This is rotation y. Do I have any syntax errors? Rotation z, rotation x, rotation y. Okay, now. So here's the thing, I'm going to do something terrible. What if I just put, if I put rotation z here, oh, I have an error. Oh, I'm missing a comma here. Thank you. So I think I got it everywhere else. Right? That's rotation z. What if I try instead rotation x? Oh, weird that that's working. I guess it's oh, you know why it's working? It's working by accident, really, because my z points. So, but I've done something incorrect. But you can see this looks as if those 2 points, and I want my angle to move up a little bit faster. You could imagine this as a plane almost spinning around the x-axis. But here's the thing. I should be doing, the projection should happen at the last moment, right? I should really be rotating first. And then I should project the rotated vector. And so here, projection and so really, for it to be correct, it's got to be in this order, because what I need to do is first rotate and then work by accident because my z values are 0. But now, let's do something. Let's make 8 points. Again, I'm doing this in a highly manual way. Let's now have all these be at negative 50. I wonder if I want to put them, I think this will be fine, negative 50. And then now these all at 50, right? I basically, right, if you think about it, a point has 0 dimensions. A line has 2 dimensions with 2 points as the bounding box. A plane, a square, has 2 dimensions with 4 lines bounding it. And then a cube is in 3 dimensions with 6 planes. But really I can kind of make the cube just with 8 points, which are the edges, all of those connections. So let me just run this for a second. Oh boy, this works too fast. I didn't want this to work so fast. So now we can see, let me just go back to rotate z. And look at this. That looks, now why do I not see 8 points? Because I'm using orthographic projection as if the light is right there. There's no kind of perspective. I'm not moving the light source away to create this kind of more 3D perspective look. I can't see when the points are right in front of each other, the shadow projects on exactly the same spot. But if I were to do rotate y, now you can see, you can kind of imagine that being a cube rotating. And here's now where I can get fancy. I can now say rotated equals mat mul rotation x times rotated. So I'm just going to do this a couple times. I'm going to just keep rotating by all the different. So I'm going to do this as separate operations. Now there's a way I could probably combine all those, but I'm just going to do all of those matrix rotations, and here we go. Now we have my cube spinning along all axes. Now it doesn't look like a cube, Time out. In all of my futzing with this, I left an extra 0 here. This rotation x should be 1, 0, 0, 0 cosine, negative sign, 0 sine, cosine. All right, so hopefully that doesn't change much. It still looks right. So that probably was just being ignored. I was ignoring it, but I don't want that in my code. So now we can see we've got this rotation. The truth of the matter is I really want to draw this as a cube. Oh, I want to draw this as a cube. Let me think about this. There's got to be an easy. Obviously, I could manually connect all the points I want to connect. Also, this is not the same size as what I started with. What I actually want to do is instead of using 50 all in here, I'm going to change every instance of 50 to just the number 1. So I'm going to kind of have normalize the cube. Actually, I kind of want to change it to 0.5. Instead of 1, I'm going to change it to, because I want the sides, the lines to be of length 1. So whoops, replace all. Ooh, that's, do I have, oh, I have 1s in other places. Bad idea. Hold on. I'm going to change all the instances of 50 to 0.5. Okay, so now if I were to run this, I don't see anything here. But very easily what I can do is at the last moment I can scale things up. And again, I could do this with some kind of, I'm just going to do multiply each vector by 100, and then I have this. And if I multiply it by 200, then I have this, which more closely matches what I started with. The angle rotations are different, but that's no big deal. Okay, I wanted to do that because I also would like to show you perspective. And I think if all my coordinates are normalized, that's going to make it a little easier to do. But before I show you perspective, let me connect all the edges. I is less than 12, I plus plus. Right? What am I connecting? I'm connecting, let me think about this. I'm connecting, if I say connect, what did I call the points? Let me just, 0 and 0. Let me write a function. Let me write a function called connect, and it gets 2 p vectors, and it just draws a line. I'm going to say stroke weight 1, and it draws a line between 1 and the other. Stroke 255. So if I were to say connect, oh, and it doesn't get 2 p vectors, it gets 2 integers, and p vector a1 equals, I'm going to call this I and j. P vector a equals points I, and p vector b equals points j. This is so I should have a line between the first 2 points. How come I don't see that? Oh, wait. Yeah. Point O. Oh, I need to connect. I need to connect. Okay, so I'm going to make this. P vector projected equals, I'm going to make an array that has 8 spots in it. And then, instead of drawing this here, I'm going to say projected. Oh, so now I really need to, this is fine. Int index equals 0. I could just use now a for loop, but index plus plus. Projected index equals projected 2D. So I'm going to put everything in an array, and then I'm going to say connect 0, 0 in projected. And then this will be an array of points. And so now this should, where's that line? Let me just make sure. Now if I say for p vector v in projected point, I really didn't want to draw the edges. This is why. I wanted to just leave it as that, leave it a viewer challenge to draw the edges. Projected 2D, projected index equals projected 2D, index plus plus, p vector v. Where's all that stroke weight stuff? This stuff should be here. Where am I drawing all the points? So, okay, there are the points again. Now, I want to connect 0 and 1. 0 and 1. There we go. It took me forever. So now I'm connecting 0 and 1. Then I want to connect 0 and 2. No. 0. Then I want to connect 1 and 0. That's the same thing. Connect 1 and 1. No. 1 and 2. This is good. Trial and error. This is fun. Then I'm going to connect 2 and 3. I just want to figure out if there's an algorithm for this. And right, because this is the plane. This is the first plane. 3 and 4. Ah, I see. So this makes sense. Whoops. No, 3 back to 0. That's the first plane. And then the next plane is the same thing, but at the end, which is like 4 to 5, 5 to 6. Oh, no, 3 to 4, 4 to, right? Because didn't I put the next plane would be 0, 1, 2, 3, 4. No. Yes. 4 to 5, 5 to 6, 6 to 7, and 7 back to 4. Okay, so that's that. Now all I need to do is connect. Oh, this is easy. So there's definitely an algorithm for this, because now I just want to connect 0 to 4, 1 to 5, right? 2 to 6. Hopefully the algorithm is revealing itself to you. And 7 to 8. No. 3 to 7. There we go. There's my cube. I have done it. Now, I should really refactor this, and I plan to do that, but right now I think I need a little bit of a break. All right, so, but this is really, actually, no, I don't. I got to do it right now. I'm sorry. This video is going to be really long. I don't care. I equals 0. I is less than 4. I plus plus. So what I'm going to do, right, there's 4 sides. I am going to connect I with I plus 1 modulus 4. Then I also want to connect projected. Then I also want to connect I plus 4 and I plus 1 modulus 4 plus 4. Let's do that. And then I just want to connect I with I plus 4. I think that's it. That's these 3 little blocks. Woohoo! Oh, I'm so glad that actually worked. Okay, so this is connecting the edges. This is going to really help when we have to do the, when we have to do the hypercube, connecting the edges. Okay, I should really go. I only have 10 more minutes in real lifetime while I'm recording this. But let's actually add perspective. Let's add perspective. How do you add perspective? Woo! So the way that you add perspective, perspective projection. Basically, we're going to add a variable which indicates the distance. Remember my ridiculous experiment earlier, like about 4.5 hours ago, if you are actually watching this video all the way to the end, where I had this light source and I was shining the light source and you were seeing the shadow here, that projection. I need a variable which is the distance away from the object, the surface that that light source is. That's how I get perspective projection, right? So to create this idea of perspective, right, I want to move the light source or move the camera further away. There's a lot of different ways to do this in highly sophisticated methods, but basically I need to scale the x, y positions by the depth, right? Objects in this mirror appear closer than they really are. Like things that are further away appear closer in. Things that are closer further out, appear further out. So to do that, this projection matrix can't just always be constants of 1 and 1 in the x and y positions. So I'm going to move this, and I'm going to, before I project, right? Before I apply before I project the final rotated matrix, I need to dynamically calculate this projection matrix according to the z value itself. So one thing that I could do is I could just say float z equals rotated dot z. And I could just try dividing by it. Okay, I'm sort of scaling it according to that z. Let's see what that does. Something, maybe it looks all weird and crazy. That's not right. Well, a nice formula for doing this is actually saying 1 divided by, this is now the distance, basically, the camera distance, the light source distance, minus rotated dot z. So if I put that in here now, and I were to say float distance equals 2, for example, now you can see this looks much more like perspective projection. So this is no longer orthographic, it's more like perspective, exactly sort of, again, I'm not saying that I've comprehensively solved every possible projection 3D way with focal length and all sorts of field of view stuff. I'm just doing something kind of basic. This is probably similar to like weak projection maybe, I think. But you can see here if I change this distance to 1, now this object appears much closer, it's more distorted. If I were to change this to 10, wow, it's so far away, but you can see there it is. Those points are a little bit too big. Now, one thing I'm not doing is changing like the stroke weight to make it seem further or smaller, but you can see I'm just altering the perspective. Okay, we've done it. Where's my train whistle? I need a train whistle. No train whistle for me. Maybe I'm going to reward myself with a piece of space melon. I have made this coding challenge. So what can you do? First of all, if you want a challenge to yourself, just go make this in 4 dimensions now. But that's what I'm going to do next. Now that I have successfully drawn a 3D cube, and just to prove the point, I am in the P2D renderer. The P2D renderer, using my own matrix math and my own rotation matrices. You don't need to do this. I would probably just go back and always use P3D. But this should let me unlock the 4th, the 5th, the 6th, the 7th dimension. Try making different shapes other than cubes. Try, you can do weird stuff. Like I probably get something like super weird if I just, let's make the distance 2 again. And let's, change this like negative to positive just for rotation Y. And look what I've got going now. I can really start to distort the world by just messing around with these numbers. What if I say 5 times cosine of angle down here in rotation Y? Okay, that's probably a terrible idea. So what kind of crazy, weird, distorted rotation perspective things can you do? Can you actually do this with vertices so you can apply fill? Can you think about color? Make some sort of weird, pretend 3D world that doesn't follow our own sense of 3 dimensions by playing with this code, and share that with me in the comments or on Twitter, and also on thecodingtrain.com there'll be a link to the webpage where you can submit user-made things.